History. All right, let's take a look at a special case of oscillations, and that is the simple harmonic oscillator. And we're going to model this with a real simple model. And this is the thing I like about this model is it applies to a lot of different situations which aren't exactly this. And we'll see that in a little bit. So the model we're going to use is this. We're going to have like a wall or something like that. And then we're going to have a frictionless surface. And we're going to have a block on a frictionless surface. So here's my block. And we're going to attach to this an ideal spring. So here's my spring. And it's attached to the block. And so right now I've drawn it at the equilibrium position. And so let's call that 0. And we're going to pull this back to some maximum value, some maximum displacement, I should say. Maximum displacement from 0. We're going to call that position A, right? So this is a different point in time, and the spring is attached to that, to the block when it's at position A. And then equally, we have a position here, which is negative A, which has the same. Let's get that right. It's about right. A negative A where the block will also oscillate between, right? So we're going to pull this back, release it, and it's going to oscillate between here and here. When it's at A, it's going to be pulled towards the equilibrium position. It's going to keep accelerating because it has an unbalanced force. When it gets to the equilibrium position, it's no longer accelerating, but it has inertia. So it's going to be continue to go even though the spring is going to push this way until it stops, in which case it'll go back to here. And it's going to keep oscillating back and forth. Now, physically, I don't have a spring that can both stretch and compress, right? In this case, in this model, this spring can stretch and it can compress. And it's an ideal spring, so the force of the spring is going to be negative kx. Because I don't have a spring that can do that, I'm going to want to create a physical situation with a cart, a lab cart, and what I'm going to do is apply 2 pulling springs on either side. So it's going to be like you can see in that video, we got a spring on either side pulling, and it will behave like a simple harmonic oscillator back and forth. I'm going to use that to help demonstrate these ideas, to show you something physical so you can actually see it. And it turns out we can ignore that second spring. So we're just going to pretend like there's only one spring acting on it when I show the cart like that. What I'd like you to do is take a look at this and plot the 3 graphs of motion for the cart, right? So why don't you get a sheet of paper out and give me a position versus time graph, a velocity versus time graph, and acceleration versus time graph. I'm going to have you start off drawing a position versus time graph. Now, let's, for this initial analysis, let's assume we pulled it back and we're at time 0, we're going to release it from this position, right? So right when I let go of it, we're going to call that, it's going to write 0. That's time 0. And then it's going to accelerate and get to here. This will be time 1. I'm just going to mark important points in time. And then when it gets all the way to negative A and stops, we're going to call that 2. And it's going to come back like that. When it comes back and it's going this way, we're going to call that 3. And then when it gets back to that position, that will be 4. And then the whole process will keep repeating. It'll keep oscillating back and forth. So what I'm going to want you to do is on your graphs. So we got 1, 2, 3, and 4. And these points in time will be equally distributed. It takes as much time to get from the max displacement to the equilibrium position as it does to go from the equilibrium to max negative A, and then same amount of time to get to here and here. And you can actually time it on the video if you don't trust me, but you should see from symmetry that it should behave like that. Because the forces, there's symmetry in the forces because the amount of force is proportional to the displacement. So it should behave like that. So, and then we're going to, of course, stack our graphs so that we can see when one's doing one thing, we can see what the other's doing. When the position's at 2, what's the velocity at 2, what's the acceleration at 2, and so forth. Now, it's real important with simple harmonic motion to not get too mathy on it and not hide behind the math. Right? You got to see how the math relates to the physical. Until you do that, you're going to really struggle with this stuff. So you got to really spend a lot of time and be disciplined early and not just get all mathy on it and try and memorize your way through some math and do something. Nah, that doesn't work very well. You always got to tie in physically what is happening. Otherwise, you're going to get into trouble. And all right, I'm going to start off just to make sure we have an idea. So I'm going to take a look at this. And at time 0, I'm here, right? And I have it's at position A, right? We call that position. So I'm going to put that here. I'm going to say this is A. And of course, we're going to get to negative A at some point. And I also want you to draw a slope. I want you to draw a slope at that point, right? So we know, what does the slope mean of this graph? Slope equals, it's dx dt, which is, of course, the velocity at that point. And maybe I'll use a different color for slope. At time 0, it's at position A, right? And I'm going to put the slope at position A. And it is, the slope is velocity, and it has a 0 velocity. So I'm going to go put it to 0 slope at that position, right? And then next, at position 1, or time 1, sorry, at time 1, it's at position 0. It's here. But its velocity isn't 0. It's going this way. And it's actually going to be going the fastest it's going to go because it's been speeding up, speeding up, speeding up here like this. And now the spring is pushing on it, so it's going to be slowing down. So this is the fastest point. It was speeding up to this point. Now it's going to be slowing down. And that is a high velocity, and it is negative. So I'm going to have a negative slope. So I'm going to go like that. All right? So why don't you go through, plot the different positions and what the slope is, and see if you can draw a curve that would make sense for that. All right? So why don't you give that a try with the position versus time graph.
Pause the video now.
All right. Hopefully that went well. Let's see what we got here. So when I got to 2, it's at position negative A. So I'm going to, I think I'm just going to plot the points to begin with. You get negative A. And then when it gets 3, it's at 0. And when it gets to 4, it is positive A. It's back there, right? So let's take a look at our slopes. When it gets to negative A, this maximum position here, it stops. So that would be a 0 slope because the slope is velocity. So it's a 0 velocity, so therefore a 0 slope. And when it gets to 3, it's going fast, so it's got a steep slope. It's in this direction. That's a positive direction, so it's going to have some sort of positive slope. And then when it gets to 4, it stops again, so it's going to look like that. So what does that look like? Now, so we see it starts here, goes here, boom, boom, boom. And if you drew a nice smooth curve, Here like that, and we got to gradually get to that, and then to this, and to that. And what does that look like? Now we didn't prove anything, but what does it look like? That looks like a cosine function, doesn't it? Looks kind of like a cosine function. Well, let's see. Let's take a look at the other ones. So now, why don't we take a look at velocity, right? Let's take a look at velocity, and in this case, I start here. The velocity is 0, and what's the slope? The slope equals dv dt, which is, of course, acceleration. So the slope of this is acceleration. Should we expect a large acceleration when the velocity is 0 at that point, or a small acceleration? Well, velocity and acceleration aren't really related, but force and acceleration are. The greater the force, the greater the acceleration. And if I stretch this the most, this is where the force is the greatest, the unbalanced force. Therefore, it has the greatest acceleration. And it is a negative acceleration, right? The acceleration's that way. That's negative. So this should have a steep slope. Oop. Let me use pink again. A steep slope, right? And negative, right? So why don't you go through, plot the points, and with the slopes to see what the velocity versus time graph looks like. All right?
Pause the video now.
Let's see. So when we get to the equilibrium position, the velocity is going fast. It's been speeding up the whole time, right? Speeding up the whole time. So, and it's a negative direction. So this is fast. In fact, it's as fast as it's going to go, because as soon as it starts moving on, the spring's going to be pushing back the other way. I'm going to call this negative V max, right? That's the maximum speed. And then I would imagine we're going to get a positive V max on the other side at some point. All right. So when it gets to 2, it stops. When it gets to 3, it's going fast again, but to the right. So that's positive. And then when we get to 4, it stops again. So it's like that. Let's draw our slopes. Thinking about forces on this thing, right? When it gets to 1, it's in the equilibrium position, so the force is 0. Therefore, the slope is 0. And then when I get to position 2, got the maximum force this way. The spring is pushing it that way. So it is positive, so it's to the right. To the right is positive, so that's a positive slope. When it gets to 3, there is no force on it. But there is we got our maximum speed. There is no force on it, so therefore the slope is 0 because the acceleration is 0 at the equilibrium position. And then finally, when we get to 4, we got the force that way, and it's a big force, so we got a big acceleration that way, and it looks like that. All right, so if we connect these in a reasonable fashion, I use blue. So that if I just get a smooth curve, it kind of looks like, that looks familiar. But anyways, let's take a look at our acceleration graph. Oh, I didn't label my axis. This is acceleration. All right, we're not going to look at the slope. The slope is jerk, but we don't really study jerk in this class. So, the beginning, right? It's at rest, but it has a big acceleration because the force is greatest. So, and it is a negative acceleration. So, I'm going to call that A max, negative A max. And this is A max here. All right. So, we're at negative A max here. Boom. Why don't you think through that, plot that?
Pause the video now.
I got negative A max, and then when it gets to 1, that is, we got 0 acceleration because it's an equilibrium position. When we get to 2, we got a net force that way, so we got a acceleration that way. That's the positive direction. So I'm going to put that there. And then when we get to 3, it's going this way. The acceleration is 0. It's at the equilibrium position. And then when it gets to 4, we got our force that way again. That is a negative force, therefore a negative acceleration. And this looks like it's going to be something like this. We didn't have the aid of the slopes as much, but hopefully we could see at this point that it probably is this. Only it should have gone through that dot. I think I'll cheat and move the dot. Not a very good drawing, but you get the idea. In fact, I'm going to redraw that. That's such a bad drawing. All right, something like that. All right, should look something like that. Now, if you take a look at this, that looks like cosine, right? That looks something like x of t equals a cosine with some argument, right? We'll talk about the argument in a second. But that looks like a cosine curve, right? Now, at this point, we're just talking about a plausibility argument. We're not actually deriving anything. We're just looking at it and get a sense of it. This is a plausibility argument. A little later, we will prove, we'll see if we can back up our arguments with some proofs. We will do that later. But first, let's start off with a plausibility argument. Now, what does this look like? Well, this looks like v of t equals v max times, that looks sinusoidal, but it's not a sine. It's a negative sine. It looks like a negative sine function. So negative with some argument. We'll talk about the argument in a bit. And then finally, we got this one, which looks like a negative cosine. So in this case, we would say the acceleration equals negative acceleration maximum times the cosine of some argument. That was just by looking at this and kind of plotting it out. And we should know that if we took the derivative of the cosine, we do get negative sine, right? We know that from calculus. And then we know if we take the derivative of sine, we do get negative cosine. So it's matching our understanding of calculus. So that's good. So now, what does the argument look like? What does the argument look like? What does this look like? Right? What do we put inside of there? Because one thing we're going to have to put inside of there is time. Right? We're going to definitely need time in there. But this couldn't be the cosine of t, right? Because the argument of a trig function has to be an angle, right? That doesn't make sense. You can't say the cosine of t. That doesn't make sense. Cosine of time? No. Trig function is, you got cosine of theta. That's an angle. Equals adjacent over hypotenuse, right? The cosine of this angle equals this ratio, right? And we had a right triangle like that. We had our theta, and there was our hypotenuse, and there was our adjacent side. So that's what cosine is, right? So this argument has to be an angle. Now, in this class, we're going to be using radians. We're going to use radian measurement. So our angles are going to be in radians, not degrees. How much time is between 0 and 4? Well, that's the period. That's the definition of the period. We got a repetitive motion, and the period is the amount of time it takes for the motion to repeat itself. When t equals capital T, t is the period, right? That's the period. The amount of time it takes for a motion to repeat itself is the period. When that is t, this argument has to equal 2 pi radians, right? Because it's made it, if this is a cosine function, it's made it 2 pi radians, one full circle around, right? 2 pi radians or 360 degrees, but we're not going to be using degrees. So, what would we need to multiply this by to have that be true? Well, if this was 2 pi divided by the period, that would give it to us, right? That would satisfy this, right? at time t equals 0, the argument would be 0, and the cosine of 0 is 1, and we would get A. All right, that's good. Now, so we get all these different cosine values until we get to the period t. We put t in there, that would drop out. We'll get a cosine of 2 pi. And the cosine of 2 pi is 1 again, right? That's where the function starts repeating itself. So this is the argument for that function. It would be a cosine 2 pi over the period times t. That's for an oscillator that we released at time 0 at position A, right? Now we can express that another way. If we remember frequency, period is the amount of time. It's a measurement of time for a motion to repeat itself. And then we have frequency, right? And frequency is 1 over the period. And frequency is the number of cycles per second. Period is number of seconds per cycle, and frequency is number of cycles per second, right? So they're inverse of each other. So I could also write this like this. I could say, well, that is a cosine of 2 pi ft. Right? And if you remember from our circular motion, if something was going around in a circle, we said its angular speed was 2 pi f. Right? That would be radians per second. Its angular speed was 2 pi f. Well, we will replace that in here, and we're going to say that we're usually going to express this like omega t, where omega is going to be, instead of angular speed, because this really isn't the speed of this thing, it is, we're going to see it's the speed of something in a little bit, but we're going to call this, in this context, the angular frequency. Angular frequency, right? And this would also be, if for this particular case, this would also be, it would have the same argument, and this would also have the same argument. Now, we don't necessarily have to start our oscillation at that point. That's not always going to be the case, right? We have to be able to start this. T equals 0 has to be any point during this oscillation. We need to be able to start this problem. We need to describe something that starts at any point in time, not just when this is at position A. Time 0 could happen when it's at its equilibrium position or whatever. So a more general function, we're actually going to do this. We're going to say, all right, we're going to describe this oscillator, x of t, equals a cosine omega t plus some phase constant. That's called the phase constant. And this is, where is this thing along this cycle when t equals 0? Because when we put t equals 0, this is going to give us a non-zero angle if this is a non-zero value. So that is, this phase constant going to allow us to start this oscillation at any given point, right? We could have started our stopwatch when the thing was at this position and going that way, right? So how are we going to figure out what that phase constant is? Well, to make this simpler, I want to also I want to draw an analogy between simple harmonic motion and circular motion. All right. So it turns out that there is a strong relationship between this and circular motion. Just like in math class, when you had the unit circle and you had you related angles to circles. It's like, what does that have to do with what does the circle have to do with the triangle, right? and you learned about your unit circle. Well, we're going to be using that again, this idea of the unit circle. And what I have here is I'm going to show you a video here where I have a turntable. Right? I got a turntable, I got an object on a turntable going in a circle, as you can see there. And if we look straight along the edge, and instead of seeing it going in a circle, look at that. It looks like it's just an oscillator going back and forth in simple harmonic motion. It is behaving along one plane, in this case, the side to side, or we'll call that the X plane, or along the X-axis. That looks like a simple harmonic oscillator. It's behaving exactly like a simple harmonic oscillator. All right, so this phase constant just tells us where is this oscillator at t equals 0. And we're going to define it by an angle. So let's take a look at the circle to see what do the angles have to do with this. Doesn't look like there's angles. Looks like it's going straight back and forth. Doesn't look like there's angles at all. All right, we got something like that. It's not a great sinusoid, but, you know, you get the idea. So it's starting at time t equals 0. It's half its maximum amplitude. And so if I wanted to create a function like that, I know that I could say that x of t equals a cosine omega t. I don't know what omega is yet. We'll deal with that later. Plus, I got to figure out what phase is this thing in, right? Let's talk about how am I going to describe this, because I'm not starting like I did the first time. The first time I started it when it was here. I'm going to start it here now. So this is what I'm going to have you do. So you always want to draw the unit circle. So here we go. We got x and y. Like that. That's more or less a circle. All right. So this would be angle 0 when it's here. This would be angle pi over 2, angle pi, and so forth as we go around. And then just as we always do when we draw this thing, it's going to go around this way. It's headed around that. This is the direction that it's going. And, you know, our angle would be like relative to the positive x-axis. So in this case, at time t equals 0, which defines the phase constant, where is this thing? Well, it's at a over 2. Well, this is a, right? This is a negative a, right? This thing is, you imagine this thing, it's oscillating back and forth, right? There's an a and a negative a. It's oscillating back and forth, right? And we're representing it by this circle, but there is no y in this case. So we're looking at the projection onto the x-axis. And we see that at time t equals 0, it's at a over 2. And a over 2 is like right here, right? That's a over 2, right? This thing is going to be at position a over 2 twice per cycle, right? A over 2 is right here. It could be going this way, or it could be coming back, right? So it's either here, or it's here, right? It's either at position 1, or it's at position 2, right? So why don't you take a moment, see if you can think about that. Where is this thing right now? Is it at position 1 or position 2? Why don't you try and figure that out?
Pause the video now.
If it was at position 1, it's headed towards the equilibrium position, right? That means it's going this way. It's headed towards equilibrium position. If it's at position 2, it's going this way, headed towards its maximum amplitude. So, well, let's see what's happening. It's at a over 2. A little later, where's it going to be? Is it going to be at the equilibrium position next? Or is it going to be at A next? Let's see. Oh, it's at A next. All right. So it's at A next, right? A little later, it's going to hit A. It'll hit equilibrium later, but first it's going to get to A. All right. So it must be right here. Right? So it's here, and This one doesn't go, this right here. It's that one right there. That's where that is. Right? Okay. It's there, right? And I didn't draw this very well. But anyways, here's my angle. Like that. If it had been here, I would draw a line there and the angle would be there. And my angle, this is the angle I'm interested in. Right there. That angle. That's where it is. Right there. It's at A over 2, which is right here, and it's headed towards A. Right? It's at A over 2, and it's headed towards A. All right? So, I got to figure that out. Well, let's take a look at this acute angle here. Use green. This acute angle right here. What angle is that? Or even if I drew this, what angle is this? I'll call that alpha. What angle's alpha? The cosine of alpha is going to give you 1/2. All right, this has to give you a value of 1/2. This is a unit circle, has a hypotenuse of 1, and we want to know what that is. We know the adjacent side is 1/2. So, adjacent over hypotenuse, what's that? What's going to give us 1/2, right? We got cosine of alpha equals 1/2. So what's alpha going to give us 1/2? That is 60 degrees or pi over 3. That's going to be pi over 3, right? So this one is going to give me, that's negative pi over 3. But really, I really want to know what this pink angle is. So that is going to be the pink angle, which I will call beta. Beta equals all the way around, which is 2 pi minus pi over 3. Right? We want to know what this angle is. This angle is all the way around minus pi over 3. So what is that? So what do we got? We got 6 pi over 3 minus pi over 3, which is 5 pi over 3. All right, so that's our argument. This is, that thing I called beta is, in this case, the phase constant. It is the angle at t equals 0. So to write this out completely for that one, it would be x of t equals a cosine omega t, we don't know what omega is yet, plus 5 pi over 3. 5 pi over. So there's our function, right? We would have values for a and omega, and it starts at t equals 0. It's at position 5 pi over 3. You need to draw your little unit circle every time. You won't be asked to do it. This is the tool you use. Right? All right. So, this is called the phase constant. The phase constant. That's the phase constant. Now, this whole thing, though, the whole argument is called the phase, right? The whole argument's called the phase. This is the phase constant, it's the phase at time t equals 0, and the whole thing is the phase at any given point in time. All right, so why don't you take a moment, find the phase at 1, 2, and 3. Remember, the phase constant is already established. It's 5 pi over 3. But what's the phase at 1, 2, and 3? All right, why don't you take a moment to do that? Draw your unit circle. Figure out what's happening. Don't just, once you get one of them to go, the answer must be the other thing. Go through the thought process every time. You need to practice this stuff till you get good at it so you can understand these oscillators. And when I throw new stuff at you, you can deal with it because you got this stuff down. You're going to need to practice this to get good at it.
Pause the video now.
All right, let's think of the phase at 1. All right, the phase at 1. So I'm going to draw my unit circle again. Phase at 1, and I got my, like this. We got X and Y, like that. The phase at 1, well, where is 1? It's at 1/2, right? It's at negative 1/2, right? And oh, keep in mind, this is a unit circle of amplitude, of magnitude A. There's negative A, and there's A. Remember, the thing's oscillating back and forth between A and negative A. And at 1, it's at negative A over 2, which is over here. There's negative A over 2. So, at 1, the particle is either here or here. One of those two. I got to figure that out. Which one is it? Well, this one, it's at negative A over 2, and it's headed towards negative A. This one is at negative A over 2, and it's headed towards the equilibrium position. Let's take a look at the graph, see what's happening. All right, so this is here. It's at negative A over 2, and it's headed towards negative A. All right, that looks like this one. That looks like that one, right? It's headed towards, because it's going around a circle like this, it's headed towards negative A. All right. So we want to know the phase angle, or we want to know the phase, yeah. We want to know the phase. We want to know the phase of that thing. All right. Well, if I want to use what I did kind of before, that's A over 2, so I'm going to look at this angle. And if I'm getting 1/2 out of this angle, right, this thing is, we got a triangle and a hypotenuse of A, and go something like that. And if I wanted to know that angle, I know that this is A over 2, right? So this angle must be, again, pi over 3, because that gives me a cosine function of 1/2, right? So this angle there, I should do it bigger, is pi over 3. Pi over 3. All right. Okay, so, but that's not the angle I want. I don't want that. I want this angle. I want that angle. All right, so what is that angle, right? Well, I know if I go all the way around to here, that is I'll call that phi 1, I guess. Phi 1 equals, this angle here is phi 1, and it is starts from here, and this all the way here is pi, but I don't make it all the way here. I make it to pi minus pi over 3, right? Because that angle is pi over 3. All right, so what do we got? We got pi, 3 pi over 3 minus pi over 3 is 2 pi over 3, right? So that phase angle is 2 pi over 3. All right. And now, this one, and you want to go through this process every time. Don't cut corners. You're not helping yourself at all. Come puking out answers. You got to help yourself. So I'm going to go through the whole process every time. Well, this thing is at In fact, I would even, erase, go through the whole process. It's not about the answer. No one cares about the answer. People do care that you can do things, though. Make sure you can do things. All right, I'm going to draw my unit circle again. Well, that's a lot of work to come up with the answer. I could have come up with it easier because I already had the answer from before. No one cares what the answer is. You got to practice this stuff to get good at it. All right. Let's see. Where are we? We're at negative a over 2. Let me put, where is a over? Here's negative a, and here's a. Remind myself, what is that? This is oscillating between here and here. All right. So let's, boom. It's at negative a over 2. So it's either here or here. Which way is it going? Let's see. It's here, and it's headed towards equilibrium position, right? Keep in mind, that's the direction, going around the circle like that. It's headed towards equilibrium position. This one is headed towards A. This one's headed towards the equilibrium position. So it looks like it's down there. Boom. And let's see what we got. Like that. Here's my, right here is the adjacent side of my triangle. So this is the angle I'm initially going to be interested in. Call that beta, I guess. Call that beta, right? And this is A. This length is A. The adjacent side's A over 2. So basically, hopefully at this point you realize that beta is going to equal pi over 3. But that's not really the angle I want. That's not the angle I want. This is the angle I want. I want this one. That's my phase angle. Right there. That's the phase. All right. So the phase is 2. Phi 2, the total phase, the whole argument, is going to be, what do we got? So if we go all the way around here, that is pi, right? So pi will get us to here, and then we had to add to it pi over 3, right? So we got 3 pi over 3 plus pi over 3 is 4 pi over 3. Right? All right. So phi 2 is 4 pi over 3. That's the phase of this thing. Remember, that is this whole argument there. And go through the process for 3. That should give you the same answer. Because if 3, what are we doing? Right? Well, if you wanted to be strict about it, you would solve that. It's the same as 1, but we have to add 2 pi to it, right? Because this has gone one complete cycle past 1. So anyway, there you go. I'm going to give you some problems with this, and you want to practice that. You want to get good at writing out these functions, understand what the function is, understand what the pieces mean. We're going to get to omega real quickly. We're not there yet, and we're going to talk about some other things too. All right, let's stop it there, I think, and then we'll move on a little later. All right, catch you soon.
Keep street.